All right, everyone. This is Sam Charrington. I am the founder of TWIML and host of the TWIML AI podcast, and I have been invited by Intel to moderate this fireside chat with Scott Clark, General Manager at SigOpt Intel. We're going to wait another 45 seconds or so for folks to finish coming in out of the waiting room, and then we will get things kicked off. If you just joined, we'll be starting in about 30 seconds. All right, everyone. Good morning and welcome to today's webinar. I am Sam Charrington. I am the founder of TWIML and host of the TWIML AI podcast. And I'm super excited for this conversation. I have been invited by SigOpt and Intel to moderate a fireside chat on experimentation and machine learning with Scott Clark, a good friend and general manager at SigOpt. Scott, say hi.
Hey, Sam. Always a pleasure to chat with you. Really excited to be talking through this topic with you today.
Absolutely. Before we dive in, a quick logistical note and an unfortunate one due to some technical difficulties. We are not going to be able to turn on video for this conversation, but we do have our smiling faces up on the screen via that slide. And as a podcaster, I'm kind of used to this audio only experience. So I am totally cool with this. I've been fortunate to have Scott on the show a few times, and this format is familiar to us both as well. I thought I'd start with a quick introduction and allow Scott to introduce himself. After early career working in infrastructure services and software, I set off to become an industry analyst about 10 years ago to help organizations understand how to best apply emerging technologies like cloud and data analytics. It was clear for me from the very beginning of that journey that machine learning would play a significant role in helping organizations really take full advantage of all the data that they were collecting. And about 6 years ago to the day, in fact, in 2 days, I released the first episode of what is now the TWIML AI podcast as a way to share the various conversations I was having in the field with the world. I've since had the opportunity to interview nearly 600 of the world's leading experts in machine learning and AI, and those interviews have been downloaded over 12 million times. As I mentioned, Scott's been a guest on the show on several occasions now, and I've had the opportunity to work with SigOpt over the years to explore several of the major trends shaping enterprise machine learning, including machine learning platforms and tooling. And our collaboration there led to the publication of my ebook, The Definitive Guide to Machine Learning Platforms, as well as TWIML's flagship conference, TWIMLcon AI Platforms, as well as now experimentation in machine learning, which is, of course, the topic of our conversation today. Scott, how about you jump in and introduce yourself?
Yeah, definitely. And congratulations on 6 years. That's incredible.
Absolutely.
Yeah. So my name's Scott Clark. I founded SigOpt in 2014 and served as CEO up through the acquisition by Intel in late 2020. Now I continue to run the SigOpt team and build out some of the AI enablement teams within Intel, trying to bring more optimization, better experimentation, and better AI to the world through Intel's AI and high performance computing efforts. I got the idea for SigOpt back in grad school as I was finishing up my PhD at Cornell. I kept running into the same problem over and over again, where we'd build a really great system, whether that was an HPC system doing fluid dynamics or genome assembly, or whether it was a machine learning algorithm trying to classify whether or not these are actually two smiling faces staring back at you or two glowering faces. And we would always ended up with the same problem where we'd build something great and we'd have to fine tune and tweak it in order to make it even better. In grad school, this meant better papers, slightly better overfitting of ImageNet to get a better NeurIPS paper. But in some of the other applications, it really meant the difference between success and failure. Were you able to assemble a genome that actually represented some underlying biological process? And in industry, I found the exact same thing, whether it was advertising systems, search systems, recommendation systems, predictive failure systems, et cetera. A lot of great work was being put into gathering data, building large systems to solve these complex problems, but a ton of time was wasted fine-tuning and tweaking them. So SigOpt was initially designed to be an optimization algorithm and service to help people tune these as optimally as possible, and has since grown into a full intelligent experimentation suite, which we'll talk a little bit about what that means in a minute. But we're continuing to live that mission of empowering the world's experts at Intel, really helping them tune, tweak, experiment, and optimize all the great things that they do to be a little bit better, a little bit faster, a little bit more efficient, and a little bit more sustainable.
Awesome. Awesome. So experimentation is a big topic, but let's maybe try to start at the beginning. I'm guessing that most in our audience have an appreciation for kind of this core idea that developing effective models for machine learning is the result of an experimentation process, and that act of experimentation is kind of fundamentally what puts the science in data science. And today we're going to explore that idea. We'll discuss some of the best practices and tooling that organizations have put in place to ensure effective experimentation. We'll talk through a vision for what's possible when all the right pieces are in place, and maybe even talk through some case studies. That said, we really want this to be an interactive session. And to that end, I've got the chat window up here, the Q&A panel up here, and I'll be keeping an eye on those throughout our conversation, whichever of those is most comfortable for you to ask any questions that you have. I would love to incorporate those into the conversation as we go. To get us started, Scott, I'd love to have you share your view on the role of experimentation. Does this idea of experimentation, kind of putting the science and data science, resonate with you?
Definitely. And I think you really hit the nail on the head. Yeah, modeling is a fundamentally scientific process. And I think it differs from traditional software engineering in that way. Instead of putting Lego pieces together to create something great, what modeling really is about is creating fundamentally new Lego pieces that then could be put into a larger pipeline to solve a business case. But oftentimes you don't even know what's possible or what you're shooting for or whatever it may be. And like any experimentation process, whether it be in chemistry or whether it be in data science, this is a very iterative process. You're doing hypothesis testing. Can this work? Does this work? You're doing iterative design of experiments where you're trying to make better and better results or get better and better understanding. And it's a very cyclic process in order to ultimately get to the point where you have the best Lego piece for whatever it is that you're trying to fit it into. And I think that this process has existed since the dawn of kind of hypothesis-driven scientific endeavors, but has only recently really come to the forefront in machine learning and AI and high-performance computing. And there's a lot of need for good tooling here in order to drive this process and make it as effective as possible.
Mm-hmm. One thing that I do want to make sure we briefly explore up front is that experimentation has come to represent a lot of different things. And one of the areas that I do often see some confusion around when having this conversation with folks, or at least a naming collision, is with the idea of online experimentation, a la A/B testing. That's not really what we're talking about here, is it?
Correct. Yeah. This is experimentation for trying to build new things as opposed to discriminate between two things. This is the experimentation that goes into tuning hyperparameters, selecting metrics, deciding which models or topologies you're going to run over, et cetera. It tends to be an offline process done with large data sets, sometimes on a Jupyter notebook on your laptop, and sometimes burning through thousands of compute hours on AWS. But it's ultimately about building something new and building the best version of something new, as opposed to discriminating between two options within a different system of should this ad be red or blue, et cetera.
Mm-hmm. Mm-hmm. I want to, this is maybe gonna come off a little bit as pushing back on this idea of experimentation as being primarily about building, although I know that you do agree with my ultimate point. We are trying to build something when we're doing experimentation, but experimentation is also really about learning about the way we're formulating the problem, about our data, about our problem space. Can you riff on that and the way that that's presented itself in your experience?
Definitely. So, well, the ultimate goal, or why many of us are doing machine learning and modeling, is to build something for our job, build something to publish a paper, build something to win a Kaggle competition, et cetera. There's many different things that go into that process. And I would say learning is a huge part of that. I think of the experimentation process as largely having three components. It's designing the experiment, kind of understanding what it is you care about, the metrics you want to track, the metrics you want to optimize, the metrics that you want to be constrained by, what you can tune and can't tune, kind of the space that you're going to be exploring as you experiment. So all of that goes into the design of your ultimate experiments. Then there's an exploration phase where you're just trying to learn as much as possible, trying to build an intuition about what you actually care about, don't care about, what you can affect, can't affect. And that exploration is really about that learning that you talked about. Then you could go back to design a completely different set of experiments based off of what you learned, or you can take that exploration into the third pillar of what I would think of in terms of this process, which is optimization. So once you've designed your space and your metrics and what you can tune and tweak and explored it to learn about what you might actually care about, then you can start to basically try to move in that direction. So you've found the map that you care about, you found the place, and that's the design. You found the place that you want to go to via exploring the map, and then optimization is about getting to that point as quickly as possible. But this is a virtuous cycle. It's very cyclic. Based off of what you learn in the optimization, you might go back and design a completely new experiment. You might go back and explore some aspect of a local optima that might be interesting or might lead to more understanding, then go back and optimize some more. And it all goes back and forth. But ultimately, the goal here typically is to do this experimentation for some business purpose, academic purpose, or whatever it may be, getting the most out of whatever model you're building, whether that be an AI or a more traditional high performance computing model.
At the risk of jumping straight to the punchline, I want to provide some additional context for our conversation by teasing out a little bit more about this idea that you referred to earlier, intelligent experimentation. Within this kind of broader conversation of experimentation in the machine learning space, there's a kind of an established category of tooling that is focused on helping folks track or manage experiments. But the part of this vision that you've been articulating is that experimentation can be so much more than a digital version of a lab notebook. Can you elaborate a little bit on this idea of intelligent experimentation and kind of hint at this vision that you're working towards?
Yeah, definitely. And yeah, there's a lot of great tools out there, and it is necessary to have that lab notebook when doing experimentation. I can't imagine people trying to effectively do drug discovery or chemistry or whatever it may be without writing stuff down. Trying to keep it in your head is a tricky thing. Although something we still see quite a bit of today, whether it's keeping it in someone's head or writing it down on a notepad or having a 10,000 cell Excel spreadsheet or something like that.
File names with hyperparameters.
Yeah, exactly. Which I'm very guilty of, again, doing in grad school as well, where we all tried to do grad student descent without version control. But that can help with the exploration. But again, because this is such a cyclic cycle, and because exploration is only one pillar of this experimentation, intelligent experimentation is about bringing all of these components together and being more than the sum of their parts. So by having tools that can help you design the experiments that you end up writing down in the lab notebook and helping you optimize the experiments once you have a better idea of what it is that you're shooting for, what constraints you might have on the metrics or parameters or whatever business case you might have. It's really the difference between having a lab notebook that's read only and having a collaborator that's helping guide you towards your ultimate goal. And I think that that's the main difference between traditional experimentation and this concept of intelligent experimentation that we're seeing people really latch onto.
Great. So let's talk a little bit more about experiments themselves. You referenced earlier hypothesis-driven experimentation, which kind of evokes its roots in the scientific process, which has been, very carefully kind of explored, defined, formulated. In the real world, though, experimentation and machine learning, often looks and feels like throwing spaghetti against the wall and seeing what sticks. I'm curious. I'd love to have you share a bit about, with the organizations that you work with, what makes those organizations that are very effective at experimentation so good at it? What are those key differentiators? And for that matter, how can we even measure effectiveness at experimentation at all? What does that look like?
Yeah, great question. I'm a sucker for analogy, so I'm gonna abuse your analogy of throwing spaghetti against the wall and see if it sticks a bit here. But that in itself is a hypothesis test. I've got a handful of spaghetti, and my hypothesis is it sticks to the wall. And so I perform the test, and I see what happens. And then I might say, okay, it did stick, but it didn't stick super long. So now I have two metrics that I care about: the binary of does it stick, and then maybe how long does it stick on the wall. And then I might say, okay, well, I can tweak certain things about my spaghetti. I can cook it more or less. I can add more or less sauce. I can use different variations of pasta and things like that. And depending on what I'm trying to do, make it stick or not stick, make it stay on the wall longer or not, all of this is basically experimentation. First, the hypothesis testing of can this work at all? Which might be that initial smoke test of I've taken a data set or a model that was overfit for ImageNet, and now I want to apply it to my data set. Can I get it to run at all? Okay, yes, no, maybe I need to change something about the input layers or the output layers. And I'm kind of just trying to see if, can it work? Can it apply to my problem? Can it beat the status quo? But then at some point you might shift into, okay, I can get it to stick to the wall, but now I want it to stick to the wall for as long as possible. This all of a sudden becomes an optimization problem. And you look at, okay, what can I actually tune and tweak about this system in order to do it? And so all of that just goes down to it's experimentation at its core. A lot of time, every field does this in some way or another. That realization that this is that fundamental scientific process that people have been doing for hundreds of years, and there is a good nomenclature and there is good processes around it, I think is a relatively new kind of insight that this field has seen over the last decade or two, but one that can allow it to accelerate and become kind of a more grown-up science like physics or biology, as opposed to the wild west of data science that I think we've seen over the last decade or two. In terms of organizations that do this incredibly well, I think it's ones that have made this insight and understanding, and start to phrase all of their problems within this paradigm of, this is an experiment, there's some goal that I'm trying to achieve, what is it that I really care about, and how do I phrase that in a way that's metrics, constraints, parameters. I obviously am extremely biased, but I can think of almost anything as an optimization problem, whether it's an organizational structure or whether it's anything having to do with computational modeling. But I've seen a lot of organizations that really think of what they're doing as a science and then apply those scientific techniques and methods as being incredibly effective at this.
We've talked kind of broadly under the umbrella of machine learning, but in the description that we have up and in some of the conversations I've heard you have, you kind of talk about AI and HPC. Talk a little bit about the HPC part of that and how it, what the interplay is with the machine learning or AI part, and how experimentation, kind of compare and contrast how experimentation happens in the different domains.
Yeah, great question. Way back when in undergrad and early days in grad school, I was much more on the HPC side of things, and then came into ML and AI in the early 2000s as it became much more popular. But I mean, I see a ton of parallels between these. It's large computational processes that are time consuming and expensive. They have a variety of inputs and a variety of outputs and a variety of tunable hyperparameters, whether that hyperparameter is the learning rate of a neural network or the step size of a finite element method for computational fluid dynamics. And ultimately, I mean, if you go all the way down, it's all just matrix multiplication and gradient descent, whether you're doing that in finite element analysis or you're doing that on a neural network. So fundamentally, these end up looking like similar problems when it comes to experimentation, optimization, and ultimately solving some of these problems. One thing that we've seen quite a bit of as well, and we're really excited to help pioneer quite a bit at Intel, is even the traditional walls between these fields is starting to crumble as well. I think people acknowledge that computational modeling is similar across it, or that, yeah, matrix multiplication and gradient descent is the fundamental kind of numerical analysis pieces that go into both of these. But we're seeing a lot of people who would do kind of historically, what I would say, classic simulation-based high-performance computing. So molecular dynamics simulations, physics simulations, et cetera, using more AI techniques at the beginning and end of their processes to help augment the data that goes into these physics simulations, to understand the data that comes out of them, so the pre-processing and post-processing, or to even help guide which types of models that they're using in general. So I see modeling as modeling at the high level, and the experimentation tools should be robust enough to be able to handle whatever it is that the person's doing, whether it's the difference between a random forest or a neural network, or the difference between a gradient boosted machine and a molecular dynamics simulation. But I also see these fields colliding very rapidly, and I see that more and more of this happening year over year. So I'll take a shot in the dark, and I'll say in 5 or 10 years, there will not be a distinction between these two fields at all.
Interesting. You referenced these experiment management tools. At their core, they're all about tracking aspects of the experimentation process and then surfacing those various metrics that are tracked and making those easier to work with on the part of the modeler. Let's maybe start by talking about, you referenced earlier some of the different types of metrics that folks want to capture in the process. Do you think that this is well understood, or is it evolving? And what are some of those?
Yeah, definitely. And I'll abandon the spaghetti analogy to give some actual real world ones. One thing that we've found is oftentimes if people only have access to a certain type of tool, they tend to fit their problems into that. And this is like, a classic management principle, and people have been talking about this forever. If you've only got a hammer, everything looks like a nail.
Yep.
But I would say it's slightly different than that insofar as some of the experimentation tools historically, while being similar, just have been maybe underpowered or not as applied as some of the tooling that exists today. So if you have a screwdriver, you might not even think about trying to build an entire house or a car, even if you can do it with a screwdriver, just because it would be too much work or it's too complex. But if you have a power drill, now all of a sudden, a lot of things get a little bit easier. Still does the same thing, it just does it better. So with regards to metrics, a lot of times when we see people trying to do this in their head, or with grid search or random search, or even with various kind of single path optimization open source tools, they might think of all of their problems as, I have to fit this into a single metric, versus looking at 2, 3, 4, 50 metrics simultaneously. Or I have to combine everything that I'm optimizing into one kind of convex combination of metrics, versus trying to find a Pareto frontier of efficient trade-offs between different metrics, et cetera. Also, we see people, especially people new to the field or coming out of academia, used to having kind of very simple metrics like accuracy, or simple benchmarks that they can benchmark against, which is the way to publish papers. And again, I'm guilty of doing this, but in the real world, it's often more complex. I need this to be as accurate as possible, but then I also need the memory footprint to be able to fit on an edge device. And then I also need the inference time to be less than a certain number of milliseconds. Oh, and then I also need it to be robust to this type of classification error, because it's being used in a medical setting. And while I care about overall accuracy, I really care about not violating this specific type of false positive or something like that. And as you start to get more and more of these metrics together, they become more complex. The interplay between them becomes more complex. You need better and better tooling. And I'd say sometimes if you're only handed a tool that can do single metric optimization or something like that, you might not even think about all the different metrics that actually go into your system. Or you might think this is an impossible problem, but we're definitely seeing this embracing of, in the real world, we're not trying to overfit ImageNet. In the real world, we're trying to solve real problems, and real problems tend to have more constraints, more inputs, more outputs, and more things to think about. And that's something we've really embraced at SigOpt. And we see a lot of firms really embracing as well too, is this applied optimization problem instead of the purely academic optimization problem.
Yeah, one of the ways that I've seen you speak to that in the past, and I'm not going to remember your specific terminology, but I thought it was interesting at the time. Like, at least what I took away from it was that often in the case of this academic perspective, not that it only happens in academia, but kind of this perspective that is optimizing these kind of low-hanging fruit metrics, for lack of a better term, like these, there are often proxy metrics or proxies for the things that you actually care about from a business perspective. There's like this this inner, think of it as like two concentric circles, or two, there's an inner loop of optimizing this proxy metric. And then people kind of forget about, hey, well, you also have to optimize the relationship between that and what you're actually trying to achieve. And that's an outer loop that is often harder to tackle. And that's why sometimes people don't get to it, but it's part of this broader process of experimentation and optimization that we're talking about.
Yeah, and I think that's the loop back as well from, like, as you go through design, explore, and optimize, that's not a linear path, and you're not done the first time you're done with that optimization step. You could learn that you were shooting for the wrong target, and you didn't know that because you've never actually hit that target. So it creates this kind of nice regularization to your problem or something like that. So you didn't realize that hitting that target was the wrong thing. But then as you hit that target, you're like, you know what? Actually, I want to shift my target, or I want to hit a specific quadrant of that target or something like that. And then so you're exploring what happens outside the optimization in order to learn that. Then you might go back and design a different experiment and then optimize again, go back and explore. But yeah, we definitely see this gathering of metrics and this setting of metrics as part of this cyclic process. Very often are you able to call out your target like Babe Ruth or whatever it is ahead of time. Even defining your metrics is iterative. And that's part of why we see this as an important process to put all together, in all honesty, by tracking, by optimizing, by exploring and designing all simultaneously. You can be better than the sum of its parts, like I said. If your optimizer is aware of this, if when you're designing things, it can be aware of the optimizer. If when you're tracking things, it can be aware of what you might eventually want to optimize, et cetera. If you can correlate experiments and learn from previous experiments and things like that, not only does it unlock this more iterative process with all three pillars, but it allows you to do each of them better than just bolting an optimizer on top of a tracker.
Mm-hmm, mm-hmm. Yeah, another way to think about that came out of a conversation with one of your colleagues. And I thought it was also really interesting that the idea kind of revolved around, I guess, something that you referenced earlier, this idea of your intelligent experimentation tool as a collaborator. And the core idea was that, as a modeler, your primary objective is to kind of explore this, space and of potential solutions and identify a solution that is going to work for your problem, for your use case. And some of that space is kind of intellectually easy for you to explore. Some of that space is intellectually difficult for you to explore. And, part of what is possible when you've got all these systems working together and in harmony is that you can let the machines explore the stuff that's easy for the machines to explore, and the human modeler kind of explore the stuff that's more nuanced, and use that as a way to, this collaboration that you're talking about, a way to partition the workload, so to speak.
Yeah, definitely. And I think, there's certain things that obviously humans are bad at. Humans are really bad at doing 10-dimensional optimization in their head, for example. And I think everybody can agree with that when it's stated in that way. But a lot of people try to do hyperparameter optimization by hand and don't necessarily think back into, like, what am I actually trying to do? And oftentimes it is high-dimensional multi-metric optimization in one's head.
Mm-hmm.
Again, if you don't have any tooling and that's all you can do, then your human intuition's probably still better than random. Although there's been studies that show that in certain cases, random is actually better than a human thinking they know what they're doing. But there is better tooling out there as well too, and it's easily accessible. But to go maybe a step deeper into this as well too, classically in physics, there's two different major branches of physics. There's theory and experiment. An experiment is about running tests, observing black holes, observing particle collisions and things like that. And then theory is about kind of explaining how and why that happened. And typically a physicist is either an experimental physicist or a theoretical physicist. And I think the idea with data science and modeling is you have to be a bit of both. And intelligent experimentation tools should help you be a better experimental data scientist because they can help you track and understand and learn and explore. But they should also help you be a better theoretical data scientist and really allow you to understand and find better results. They should make recommendations. They should see some of these correlations that you're not able to see. They should help drive you via recommendations to better and better solutions. And so in my mind, intelligent experimentation as applied to data science or modeling or HPC more generally is about being both that experimentation oriented scientist, but also give you the tools to be a better theoretical scientist as well.
I want to take a moment to remind folks in our audience that we do want this to be interactive. And if you have questions, feel free to drop them in the chat or the Q&A panel. Either one is fine. Scott, I want to have you speak a little bit to the main types of challenges you see organizations running into when they're trying to build out their experimentation processes or trying to kind of climb this, curve of maturity and build better experimentation into their modeling capability.
Yeah, great question. I mean, one of the first problems we often see is people just even knowing what's possible. And I hinted at this a little bit before of like, if you've only ever done optimization by hand, then you might try to fit all of your problems into a 2 or 3 dimensional space of like, we can only vary a certain number of things at a time because we're doing grid searches or parameter sweeps or whatever naive method you might have used before, or you might only be able to think of a single metric at the same time because that's the thing that's easiest to visualize, or you can shoot for a single peak instead of trying to find a set of things that trade off various constraints and metrics efficiently. And so sometimes it's teaching people that you can expand that problem. You can tune the hyperparameters simultaneously with the transformations of the data and simultaneously with the topologies and things like that, that you can really widen that space, that you can start to think about more metrics, that you can actually put constraints on the metrics themselves. I care about accuracy, and then I want this to be below a certain threshold of maybe memory footprint, but under that threshold, all memory footprints are equal to me because I don't get any extra credit for using 80% of the device. 80% and 90% is equivalent, but I want the highest possible accuracy. And so I think it's really showing them, if you never click the button on the power drill, you can twist the power drill around and it's just a really unwieldy screwdriver. It's teaching them how to use that power drill and what it can actually do as well too. So I think that's maybe the first step, is that things that were impossible before or intractable before are now possible. And then it's really the next big step is thinking about the metrics themselves. So it is very easy to use these classic proxy metrics, as you said, things like accuracy, things that make better academic papers or are easy benchmarks for comparing different methods. But in the real world, if you're doing algorithmic trading, if you're doing drug discovery, if you're doing predictive maintenance, they all actually want to do slightly different things, and they all have different objective functions that they're trying to optimize. And there's a whole field in operations research around objective function solicitation, or what is it that you actually want. But I think that's the next step that we see firms doing. The things that a lot of them struggle with is if you could actually have this model do whatever it is that you want, what would that be? And oftentimes it's not, well, I just want it to blindly have the best F1 score or something like that. And articulating that and quantifying that can be a difficult problem. But when done, now all of a sudden you have this great target. It can be a way to motivate the engineers, because now they can see how that impacts the actual business. And it ultimately allows you to set all of these problems up as optimization problems and hit that target efficiently and effectively. I'd say those are the two big things we typically see: is what's possible, and then what should I actually be going for? And then the rest of it, as we've already discussed, is around just thinking about this as a scientific endeavor backed by experimentation, as opposed to traditional software engineering. Just plugging together the Lego pieces that kind of fall out of NeurIPS or ICML or some of these other conferences, but really trying to build what's right for each application.
The first of those challenges sounds like an education problem and an awareness problem. Is the second as well, or are there things that you've helped folks walk through, or processes or approaches that you kind of point folks to help them develop that their ability to think differently about the way I think I'm hearing is ultimately kind of problem formulation, right?
Yeah, it's really that design of experiments, that first pillar in that cyclic process. I think education's a great part of this. Thankfully, we work with great partners like yourself that have great ebooks that help educate people on this, and have great webinars. But I think that's been coming along again. We've been talking for many years, all the way back. Maybe I probably wasn't the first, but 5-6 years ago. And we've both seen this field mature quite a bit in terms of the way people are thinking about these problems and what it may be. But yeah, so education's a huge component of it. In terms of how we help people beyond that education side of things, is the tool itself should help pull people along. So often on the second point, when it comes to metrics, we'll encourage people to track everything. We'll encourage people to start putting constraints on things. We'll encourage people to optimize multiple metrics simultaneously. And it's often interesting when you're looking at a metric that itself might be a composite metric, like an F1 score or something like that. When you have people optimize the individual components, and then you show them like what we were shooting for before, but all of these other options along this kind of efficient Pareto frontier, this efficient trade-off between these metrics, and say, well, did you actually want this, or did you want this other trade-off? If I'm blindly shooting for accuracy and the model takes 10 seconds, a 90% accurate model takes 10 seconds to do inference, and an 89.9% accurate model takes 1 second to do inference, which one do you actually care more about? And that can be this aha moment for people of like, oh, wait a minute. Yeah, I would totally give up 0.1% in accuracy to make it 10 times faster. But again, if you're only blindly shooting for that one metric, you might not even know that that's possible, or that's even something that's feasible with your model. And so it's really taking things that were either held constant or just held as oh, I'll calculate this metric after the fact, and having people track it up front, constrain it up front, optimize it up front. That can be a huge aha moment for kind of opening up the space of possibilities. And that can be done both through education, but I think seeing it live is often what I see people really latching onto.
Awesome. I want to take another opportunity to invite additional questions from our audience. And while we're waiting for any of those that come in, you've kind of sprinkled some examples throughout, but I'm wondering if there's maybe a richer case study you can talk us through of, in particular, this idea of like, not knowing that something was possible through the kind of intelligent experimentation that we're talking about, and having that realization, getting there, and then what that enabled. Is there a case study that comes to mind that you can talk through?
Yeah, definitely. I would recommend, so I'll go through a specific example, but as I mentioned before, a good experimentation tool should be agnostic to the underlying method. So we have many more examples on our website. We recently ran a summit that had people from a wide variety of fields, academia, industry, doing things like graph neural networks and computer vision and NLP, all the way to physical simulations. So if there's something that resonates with you, I'm sure we have an example for it, you being the listener here. But I'll give one specific example here. So we recently worked with this firm, Novellus. They were trying to design a better aluminum can. And this is kind of a classic optimization problem of like, can you use slightly less aluminum or whatever it may be to get the exact same volume? And there's lots of fun articles online about students trying this and then like sending it to Coca-Cola and them being like, well, we've actually done this quite a bit and this is as good as it can get for various reasons. But that's a perfect example just in itself that oftentimes maybe in your mechanical engineering or materials class or something like that, it is possible to make an aluminum can that has the same volume using less aluminum. But it turns out there's a constraint on the manufacturing process itself. And when you add those two metrics together, what Coca-Cola has come up with over the last several decades is actually optimal with all of these different constraints in place. But we were working with this firm, Novellus, and they were trying to not only solve the problem of the cheapest possible aluminum can, and also one that could satisfy all the constraints of the manufacturing process. But they wanted it to be able to stack better as well, because a can needs to be able to deliver a liquid, but it also needs to be able to sit on a pallet and be delivered as well too. So this is one more metric on top of an already complex metric space that they wanted to tune and tweak. And so they had a simulation to be able to determine whether or not the outputs of various designs. They went through a traditional design of experiments, which looks kind of like a grid search or a random search. And what they ended up doing was calculating all of the metrics they might care about after the fact. So running through this process with a bunch of different permutations, and then seeing, okay, which ones actually satisfied all the things we care about, and then of the ones that satisfy our constraints, which ones did the best on these specific metrics. So there was no kind of feedback loop here. There was no, I've learned this from these specific configurations. How do I take that learning to try the next thing more intelligently? How do I guide my way through this space? So they did about 15,000 simulations using that traditional technique before they came to us. And then they were able to bootstrap their experimentation with us by loading in that previous data. One nice thing about an intelligent experimentation method is it should be able to take all inputs, whether it's previous experiments you've run or hybrid optimization, where some of it might be coming from your head, or an open source optimizer, some of it might be coming from the SigOpt optimizer. It should be able to allow for all sorts of asynchronous inputs, basically, and learn from all of them, so it can be better than the sum of its parts. But basically, after running those 15,000 simulations, they had something that worked pretty well, and they were going to go to production with it. And they ran 99 simulations with us. And within those 99 simulations, we were able to find a configuration that was 15% better on their main ROI metric than they were able to do with the 15,000 before. So this obviously had a great business outcome of 15% better versus the other techniques. It was 99% faster in terms of CPU time and wall clock time. And ultimately, as data centers get more and more expensive, there's 99% less carbon footprint as well. People are starting to equate CPU time with carbon time as well, and get to that better result. And this kind of shows the difference between the historical approach to experimentation of try different things and calculate it after the fact and then do a sort, versus doing this kind of intelligent, iterative process in order to drive to the best results.
Fantastic. That's such a great story. And I'd encourage folks I had the opportunity to check out the Novellus presentation at the SigOpt Summit. And maybe you can follow up with folks on how to find that. But it's a really interesting presentation among many others there.
Yeah, I think it's summit.sigopt.com, or just search for SigOpt Summit in Google and you'll find it. All the videos are online. And yeah, we had some really good talks.
Awesome. Well, Scott, as always, it's been wonderful chatting with you about this topic. I learned a ton, as I always do when we get together and speak, and I'm sure our audience did as well.
Thanks, Sam. It's always a pleasure.
My pleasure. And thanks everyone for joining us.
Thanks.